All right, let me get started on this question. This is one of the projectile motion questions from actually way back early in the semester. I'm just going back and doing these new questions that I put in at the in the problem set 2, so that I can edit it, have this available as a homework help video to students next semester, like at the beginning. So, by the way, because this is a long question, let me scroll down a little bit. This is from out of chapter 4, 2D kinematics, problem 45. It should be projectile motion. That's how I picked it. So, a rock is so let me start sketching as I read the question, just to make sure I have a good understanding of the physical setup of the question, that I have a correct mental image. It sounds like I have a cliff, and it says a rock is thrown off the cliff at an angle of 44 degrees with respect to the horizontal. I'm going to assume it's a 44 degrees above. It's probably, and I'll label it theta. 44 degrees with respect to the horizontal. The cliff is some height, 100 meters, capital H. The initial speed of the rock is given, 25 meters per second. All right. How high above the edge of the cliff does the rock rise? Okay, it looks like the question is gonna ask me a bunch of questions. So let me just proceed through it methodically, carefully, not skipping steps. So when you have a projectile motion, one of the first things you want to do is break your motion into horizontal, X, and the vertical components, Y. Later on, when we do forces, sometimes you'll want to pick X and Y axis differently, like a tilted and whatnot. With a projectile motion, straight axis is how you should pick it. There's a reason for it. So these are some of the key equations that you will be dealing with when you're dealing with the projectile motion. And with the axis defined this way, the X component of acceleration is 0. Constant velocity in the X direction. That's sort of a defining feature of a projectile motion. We ignore air resistance and all that. And from that means your whatever initial velocity you had in the X direction is constant. So the displacement in the X direction is simply your initial, oh wait, I didn't mean to say initial is constant. The X component of velocity is constant at the initial value. So the displacement in the X direction is just the initial in the X direction times whatever duration of time. That's it, pretty simple. It's in the vertical direction where you get more interesting motion. The acceleration in the vertical direction is minus g, downward, that gravitational acceleration. So you're gonna get these two time-dependent expressions. For the speed in the y direction, as a function of time, it's gonna be some initial speed, whatever you had, minus g times t, and the y position, consistent with this constant acceleration, will be whatever y position you had, plus the part that's attributable to the initial speed, v naught y times t, and the part that's attributable to the acceleration, minus 1/2 gt squared. We covered these kinematics formulas with the constant acceleration. And projectile motion is one kind of good source of examples because of this constant acceleration. So, all right, with all those in mind, let's just work through the question one step at a time. The first part asks, how high above the edge of the cliff does the rock rise? So I'm imagining this kind of motion. With this initial velocity, the rock is going to undergo this kind of trajectory of motion. So I can imagine there being a highest point that the rock reaches. And the question is asking for this delta y here. Okay. So there are some conditions that's given subtly in the statement of the question that you have to learn to recognize and apply. So whenever you are looking for highest point like this, in the question, it asks how high above like the highest point, then what it's telling you is that at this position, your speed in the y direction is 0. It comes from calculus. It's neither moving up nor down. You can imagine taking a derivative of this, and like it maximizes or extremizes the height. So that's the condition you have. With that in mind, I think I can use this equation to try to solve for time, and then plug it in here to get it. There's another equation that you could use. Let me just point it out, and you might use it. The other equation that you might use that's useful is what's sometimes called the V squared formula. That tells you that V final squared is equal to V initial squared plus 2 times acceleration times delta x, and you can apply this in the y direction to get basically delta x. But this time, let me just go the longer set of steps. So I'm gonna start out with this as my equation 1 and plug it into my equation 2. So equation 1, let me write down the version of the equation with all the parameters put in. My final y speed, or at this position, is going to be 0. That's equal to my initial y speed. Okay. That I need to, so my v vector, I need to imagine breaking it up into components, x component and the y component. This is my v naught y, v naught x. And I remember the trick stuff. So, ka, toa. Sine is the opposite over hypotenuse. Cosine is adjacent over hypotenuse, and so on. I want this, which is opposite. So I use the relationship sine of the angle is the opposite, v naught y over v naught, the speed given. So solving it for v naught, I'm going to use that. V naught times sine theta, that's my initial y speed, minus g times the whatever time the particle reaches this, the rock reaches that position. So let me solve this for t. Solving it for t, just doing the algebra in my head in the interest of time. T is equal to v naught sine theta divided by g. I can plug that into equation 2. So from equation 2 and what I derived from here, I get let me call this delta y. My delta y, which is y at time t minus y naught, that's equal to the initial velocity part, v naught sine theta, and where I have t, I'm going to plug in this expression, v naught sine theta over g minus 1/2 g times t squared, v naught sine theta over g squared. And you actually see beautiful simplification, because these two terms, v naught sine theta, v naught sine theta, they are the same. So I can combine them as v naught sine theta squared. I have that here, v naught sine theta squared. And once I distribute the square, this g squared cancels out one factor of g here. So these two terms are actually the same, some term minus half of the same term. So this ends up being 1/2 plus 1/2 times v naught squared sine squared theta over g. And you can do dimensional check, check the units, make sure you get number in units of meters. Let me plug in the numbers and make sure I didn't make any mistakes. Here's Wolfram alpha. So 1/2 or 0.5 times v naught, that was 29. I think I can plug everything in basic SI units, so I'll just keep just the numbers in basic SI units. So 29 squared times the sine of 44 degrees in angles squared divided by g, 9.8 meter per second squared in basic SI units. And with that, I get 20.71. I should be able to round it to 3 significant figures and get it graded as correct. 20.7 meters. Alright, that seems decent. Nothing Okay, let me move on to the next question. How far has it moved horizontally when it is at maximum altitude? Ah, okay, good. So I made a good choice without having read ahead to have worked this out. Because if you had used this v squared formula, then you would basically have to do this anyway for part B. So I didn't read ahead, but I made a good choice. So I'm going to use this as my equation 1 prime and plug it into equation 3, which will give me how far it has traveled. So delta x is equal to the v naught x. Oh, so from here, I have, this is the adjacent side. So from cosine is cosine theta is adjacent, v naught x over v naught. I can solve this for v naught x. That's gonna give me v naught cosine theta. That's my v naught x times delta t, or the amount of time. That's gonna be v naught sine theta divided by g. And there are ways to simplify it. This, sine theta times cosine theta, that is, 1/2 sine of 2 theta. You can simplify. You also don't have to. This is a perfectly fine expression. Into this expression, I can plug in all the numbers, get an answer to check. So let me do that. All right. So here, can I reuse any of it? Oh, I guess I can reuse the v naught squared. Let me get rid of the 1/2. And I have sine of the angle, and then I need to have it as times cosine of the angle, and I'm still dividing by g. Yeah, 42.9. That sounds about right, horizontally. Okay, good. Let's keep going. How long after the release does it hit the ground? So don't do the thing that I might have done, just plug in numbers here. No, not what they're asking. Now we are looking for a different moment in time. We've been answering questions about what's happening at this top here. We are now being asked for what's happening at this moment in time. Let me call that snapshot B. So how long after the release does it hit the ground? I don't think I can use this anymore, because when it's hitting the ground, my v naught is not, the speed here is not 0 anymore. So I need a different condition. Let me make some space here by erasing some of the expressions that I don't need. Okay, so in snapshot B, the condition I have is that it's hitting the ground. I might say, that's where the position is 0, setting 0 to be, at the ground. So I think I'm going to actually use my second equation that handles the second equation that handles the projectile motion. Let me call this my equation 1 for this part. So in equation 1, I can plug in my final y height is 0. And that's going to be equal to my initial y height starting from h, plus the initial velocity. I worked it out before. v naught sine theta times time. Yeah, I think I have to leave that in. Don't know time yet. I'm trying to solve for it. Minus 1/2 g times O times squared. All right. So I don't like using quadratic formula, and I'll try to avoid using it whenever I can. And this is one of these situations where I have to say I can't avoid using it. So I'll have to use quadratic formula. So hopefully you have it memorized. It goes as, in equation like this. This is more or less in the standard form. So this is what we call A. This is what we call B, coefficient to the linear term. And this is what we call C. So with these coefficient designations in mind, the time t, the variable, is given by b squared, minus b, plus minus square root of b squared, minus 4ac, square root of whole thing, divided by 2a. So that's the formula. I'm gonna use it. There's no real other way to do it here, other than maybe using computer algebra system and something else that does the algebra for you. I guess you could. So t is equal to let me put this in. Minus v naught sine theta, that's minus b, plus minus square root of this thing squared, v naught squared sine squared theta, minus 4 times a times c. So 4 will cancel out, portion of 4 will cancel out 1/2. So it's minus 2 times a g. Oh, and minus times minus, it's plus times c h, square root of the whole thing, divided by 2a. So that's going to be minus 2 cancels 1/2, so g. And you could simplify it here, but from here I can just, or it doesn't really simplify. So let me just plug in the numbers. Yeah, now if you are wondering about this plus minus business, try plugging in both the signs. Let me give you this a try. So minus v naught 44 meter per 29 meter per second times the sine of 44 degrees. This time let me try plus square root of v naught 29 squared times sine of 44 degrees squared plus 2 times g, 9.8 times h, which was 100 meters basic SI units. All of that divided by minus 9.8. So whenever you plug in these numbers, so quadratic equations, you're going to get 2 roots in most general case. And oftentimes, one of those roots will be unphysical. It might be a negative time when you let, t equals 0 be your starting point. So when that happens, try the other side, minus here. Now I get something that looks sensible, 7.02 seconds. That's probably right. Let's give that a try, 7.02. So that's correct. Now, if you are satisfied with simply discarding the other solution, then sure, yeah, that's fine. It was unphysical. But you might wonder, like, what's that about? Where is that coming from? What that represents, it's representing this kind of hypothetical path that didn't happen. So this rock, instead of being launched at t equals 0 from here, it could have actually gone from way over here and got launched here with some different speed. At t equals 0, reached this point and continued on this trajectory. For that hypothetical scenario, that's what negative time is giving you. But it's unphysical. That didn't actually happen. So we throw that out and just keep the physical solution. All right, let's try wrapping this question. It's long. What is the range of the rock? So here actually part C helps us, because we worked out the time, so we just have to use this, take the time, multiply that to v naught x, that'll give us the range. Let me actually just do that in Wolfram alpha. So this is my time at which rock hits the ground, so I'm gonna multiply this whole thing by v naught, so 29 meter per second times cosine of 44 degrees, and that should be the range, 146 meters. Good, let's keep going. What are the horizontal and vertical positions of the rock relative to the edge of the cliff at all these times? Horizontal and vertical. I think one of these is supposed to be y. I'm guessing it's the second set of numbers. Let's give it a try for t equals to, and actually let me do the calculation this way. I'm gonna kind of use alpha of, so here I don't actually have to do any algebra anymore, because I can just use this expression and this expression as written. We are being given the time and all the other parameters we know. So the way I'm gonna do this is I'm gonna do this as a kind of a tuple calculation. The first element of the tuple will be the position. So v naught x, that will be 29 meter per second times cosine of 44 degrees times the time. They gave us 2 seconds in basic SI units. That's my x. My y will be initial height h, 100 meters, plus the v naught y, that's 29 times the sine of 44 degrees times the time. They gave that to us, 2 seconds, minus 1/2 times g, 9.8 meter per second squared, times the time, 2 squared. So if I press enter, it should give me both the numbers basically. Coordinates, yeah, it's giving me that coordinate, 41.7, 120.69. 41.7, 120.69. Good. Wait, why isn't that correct? Oh, maybe it's possible. Oh, no. It's because I went too fast and didn't read the question. It said relative to the edge of the cliff. So for my Y position, they actually want so the landing position, with the coordinate system that I set up, I was saying, bottom of the cliff is at Y equals 0. For this part of the question, they don't want that. Let me erase this so it doesn't confuse me. For this part E of the question, they actually want this to be Y equals 0. So here, it's actually going to be Y equals minus H. So for my initial Y height, I have to put in Y equals 0, because that's how they want to set up the reference. So let me fix that here. It's gonna be no 100 there. So I'll get some negative answer at some point, and that's fine. I got 20.69. Probably. Oh, I could have just subtracted it, probably. Lazy. Alright, that looks good. And I'll reach out to the question author about fixing that letter. Let's do the rest. It's a simple substitution in the Wolfram alpha expression. Alright, we are looking at 4 seconds. So let me replace all the 2's with the 4's. And I get a coordinate, which will be at, hard to read, 83.4 and 2.18. Yeah, it's just a level with the cliff, and then after this I'll get negative answers, I think. Let's actually do that and submit them all. It's probably, right, 6. Replace all the 4's with the 6's. And I get, yeah, now it gets negative height. 125.2. And for physicality, this number should not be more negative than minus 100. Like if they gave us t equals 8 seconds, then it's a trick question. The rock already landed. So 125.2 and minus 55.5. Yeah, that should be correct. Good. So that's all the parts. It's a kind of long, detailed question that hopefully helps you understand how to analyze any projectile motion question.